One of the good things about radians is they simplify a lot of formulas to do with circles. So for example, arc length. So here's a diagram of a circle below, and an arc is a portion of the circumference. So if we cut out this section of the circle here, like a pie, this section of the circle would be referred to as a sector, and we'll talk more about this in a moment. By the way, in order for it to qualify as a sector, it has to originate from the center here. So something like this, for example, wouldn't count as a sector because it doesn't originate from the center. But every single example that you are going to meet, it will originate from the center. So you don't really need to worry about the definition of it too much. And then this edge here of this sector, this is the arc here. Technically in this diagram we've actually got another arc as well. We've actually got this bigger one here that is made up of this bigger sector here. But let's not worry about it. Let's worry about this smaller arc here of this sector here. So if the radius of this circle, which is this line, is also this line, because they both originate from the center here and they go to the circumference, that's the definition of the radius. If the radius of this circle is r, and the angle between these two radii is theta, if theta is in radians, this is important, it has to be in radians, then the length of this arc here, which we're going to call L, the length of this arc is simply going to be the length of the radius multiplied by theta in radians. And you can see this is a really simple formula. The length of this arc is just the length of the radius multiplied by this angle in radians. Now, if this angle was instead in degrees, this formula would become a lot more complicated. So what we would have to do, so the circumference of a circle, hopefully you know this, circumference of the circle is equal to 2 pi r. So this is this entire edge here, but we're only interested in this part here. So what we would have to do, as the entire circle is 360 degrees, but we're only interested in the theta section here, therefore the length of this arc here will be the circumference 2 pi r, but we would multiply it by theta over 360. So for example, if we were interested in the entire circumference, this angle would therefore be 360, so it'd be 360 over 360, so therefore it would just be 1, so therefore it would just be 2 pi r here, which is the circumference of the circle. If we were interested in half the circle, for example, like this, a semicircle, this angle here would be 180 degrees, so it'd be 180 over 360, which is a half, so therefore it would be half of the circumference here, and therefore you can see that this formula does work and you can see where it comes from. But you can see that this formula is a lot more complicated than this formula here, to the point where we don't even worry about this. We're never going to calculate this in degrees. We can just calculate it in radians and use this a lot simpler, or a lot simpler formula here. This formula is not given to you in the formula booklet, so you have to remember it, but as you can see it's really simple, so it's not that big of a deal. So here's just a basic example where we're told that the circle shown below has a radius of 4, and given an arc subtends an angle of pi over 6 radians, find the length of the arc. So okay, all we just need to do is find the length of this arc here, which we're going to call L. Now the word subtends, they love using this word. The word subtends just means opposite. And you can see how this works. It says an arc subtends an angle of pi over 6 radians, aka an arc is opposite an angle of pi over 6 radians, and you can see that this is the case. Here is the angle pi over 6 radians and the arc is opposite it here. So that's all the word means. It's not really that important, but just know that if you need to. And because this is in radians, because of this rad here, therefore we can really easily do this by just doing L is equal to r theta here, where r is equal to the radius, which is 4, and theta is equal to pi over 6. So therefore L is equal to the radius, which is 4, times theta, which is pi over 6, which is equal to 2 pi over 3. You can probably leave it like this if you want to, but if it asks, it doesn't ask here, but if it asks something about decimal places or something, you put it into a calculator, and this is equal to 2.09. So the length of this arc here is 2 pi over 3, or 2.09. So here's another example where we have a circle that has a radius of 4 and an arc that subtends an angle of x. So this is the arc they're talking about here, that subtends at an angle of x like this. And it says given that the length of the remaining bigger arc is 20, so this is going to be this remaining bigger arc here like this. Given that the length of this is 20, find the value of x here in radians to 2 decimal places. So let's focus on this arc to start off with, the bigger one. So remember, the length of an arc is L is equal to r theta. Well, we know the length of this arc here. We're not including this section here. We know the length of this arc. It tells us it's 20. And we also know that the radius of the circle is 4. This is still going to be 4 here. The radius of the circle is the same throughout, so this is still going to be 4. But we do not know this angle here of theta. This isn't including this x part, it's only this part here. We don't know this angle of theta. So therefore we can find this because we know the length and we know the radius. So therefore it's going to be 20 is equal to the radius, which is 4 times theta, and then divide both sides by 4 to get that the theta is equal to 5. So this theta angle here is equal to 5, and therefore we can figure out this value of x here, because remember that the entire angle is going to be 360 degrees. When you go all the way round, the angle is 360 degrees. So therefore x is going to be 360 degrees minus whatever theta is. So 360 degrees minus theta will leave us with x. But remember, we're working in radians, so it's not going to be 360 degrees. Remember that 360 degrees is equal to 2 pi. So therefore x is going to be the entirety of the angle, which is going to be 2 pi minus theta, which is 5. So x is equal to 2 pi minus 5, which if you put it to your calculator, x is equal to 1.28, to 2 decimal places. So that's the way that you do it. You find this angle theta here, use the knowledge of this whole angle here will be 360 degrees or 2 pi, and then subtract this section to get the remaining section, which is x. Another formula that's really simplified by radians is the area of a sector. So a sector is just a portion of the circle. So this edge here is the arc, as we said, and this whole thing here is the sector. If the radius of the circle is r and this angle here is theta, and if theta is in radians, then the area of the sector is equal to half multiplied by the radius squared multiplied by theta, if theta is in radians. This isn't given to you in the formula booklet, so you'll have to remember it. And again, this is a lot simpler than if the angle was in degrees. If the angle was in degrees, recall that the area of a circle is equal to pi r squared, but this is the area of the entire circle, but we're only interested in this small section here. So the area of the circle would be pi r squared, and as we consider the entire circle to have an angle of 360 degrees like this, and we're only interested in the theta section, it would be theta over 360 multiplied by the area of the circle. This is the same as what we did for the arc length as well. And because this angle is, because this formula is so much simpler, we never worry about this. We only use it in radians and this version here. So here's just a really quick example just to plug some numbers in. So we have a circle with radius of 7, and we have this angle here of 3 pi over 4, which it tells us is in radians, although because it's in terms of pi you can kind of infer it's in radians. And we need to find the area of the sector, so we need to use the formula A is equal to half r squared theta, where r is equal to 7 and theta is equal to 3 pi over 4. So therefore the area is equal to half times 7 squared times 3 pi over 4, which if you put into a calculator, the area is equal to 57.73. Now, almost all of the questions that you will be asked will want you to find the area of something called a segment. Now, a segment can take many forms, and there is a specific definition for a segment, which I'm not going to bother with here, it's not that important. For the sake of this chapter and video, a segment is part of a sector, or it could also be a shape with a sector inside of it. Now, there's loads of ways they can do this, so here's some examples, where the shaded regions here are the segments, and you will need to find the area of these segments. Now, they look kind of complicated, but the trick is to find a sector which will always be present. You need to find some sort of sector, and you also need to find some sort of simple shape such as a triangle. And what you have to do, you have to minus one from the other in some sort of way, and what will be left is just the area of the segment. So let's do this example on the left to start off with. So the first thing that you need to do, as I said, is find some sort of sector. And hopefully you can see that if you look close enough, the sector is here. This is 2 radii. This is this is part of the sector, and this is the arc here. And this whole thing, hopefully you can see, is a sector. And now we need to find some sort of simple shape, and hopefully you can see that there is a triangle present here. This is one of the sides, this is one of the sides, and this is one of the sides. So there's a triangle present. And in order to get this area here, you can do the area of the sector. So the area of the sector is this whole thing, minus the area of the triangle, which is just this here. And hopefully that you can see, if you do the area of the sector minus the area of the triangle, the only thing that will be left is this section here, and therefore that will give you the area of the segment. So let's do this example on the right here. So firstly, we need to find the sector, and the sector is this here. This is 2 of the edges, and this is the arc here. Sometimes they will give you the sector without actually like giving you like the rest of the circle like this, so that this is still a valid sector with kind of these 2 things here sort of being the radii here. And then we need to find a simple shape, and hopefully you can see that this whole thing is a triangle. So therefore we have a triangle. And we need to find this shaded region here, the area of this segment, and we can do this by doing the area of the triangle, so this entire thing here, minus the area of the sector, which is this here. And if you do that, the only area that will be left is the segment here. So you cannot figure out the area of the segment directly, you're going to have to minus things from each other. And that's how you do it. Find the sector, find some sort of simple shape like a triangle, and then figure out some sort of formula for minusing them from each other in order to find the segment here. The sector, the simple shapes such as the triangle, can be inside the sector, such as this one here, or the sector can be inside the triangle, such as this one here. Now, I know you might be thinking is how do we actually find the area of the triangle and the area of the sector, and you will be able to do this. The area of the sector, we talked about it before, you find the area of the sector using the formula half r squared theta, when theta is in radians, and there's loads of ways you can figure out the area of the triangle. You can figure it out using half AB sin C, like we did in first year, or you can just do half times the height times the base. There will be a way for you to do it, which we're going to go through a load of questions so you can see how. So here's the example that was on the left. I've just expanded it and included some values so we can actually use it as a question. So we need to find the area of the shaded region. So firstly, we need to find the sector. I know we've already done this, but just do it again. So the area of the sector is, so this is one side, this is another, and then this here is the arc. So that's the sector, and then we need to find some sort of shape, and we can see this triangle here. So we have a triangle, and the area, so the whole thing is the sector. It's the area of the sector, and then we can minus the area of the triangle here to just be left with the shaded region, which is what we want. So the area of the triangle. So now we actually need to find these two areas. So let's start with the sector. So remember that the area of a sector is half r squared theta. So r here, we're told that the radius of the circle this side here is 5, so r is equal to 5, and theta is this angle here. It's already given to us in radians, it's 2 radians, so therefore this is 2. So therefore the area is equal to half times the radius, which is 5, and then squared, times theta, which is 2. And if you put this into a calculator, this is equal to 25, like this. And now we need to find the area of the triangle. So we have this side here and we have this angle, but remember that this is also the radius, so this here is also going to be 5. So that means we have two sides of the triangle and the angle in between. Go back to year 1 if you need a reminder for go back to the area of triangles video. But when we have two sides and the angle in between, we can find the area of the triangle using the formula of half AB sin C, where A is 5, B is 5, these two sides here, and C is equal to 2 radians. So therefore the area is equal to half times 5 times 5 times sin 2. Now you can just put the radians straight into your calculator as long as your calculator is in the radians mode. I talked about what this means in the previous video, so go back to that if you need to. But you are allowed to just put this straight in if your calculator is in the radians mode. If not, you'll have to convert to degrees, but just put your calculator in the radians mode and you can just put it straight in. And therefore, if you put this into your calculator, the area is equal to 11.37. So the area of the segment is the area of the sector minus the area of the triangle. So it is going to be the area of the sector, which is 25, minus the area of the triangle, which is 11.37. And if you put this into a calculator, this is equal to 13.63. So the area of this segment here is 13.63. So I'm going to dedicate the rest of this video to just doing past paper questions because there's loads of them available, because there's loads of them in the old spec, and I think there's quite a few good questions as well. So here's an example of this where it's actually kind of a modelling question where it kind of talks about like a flag consisting of a triangle and a sector. With these kind of wordy questions, I always make sure that all the information here is in the diagram because I base my kind of like working on looking at the diagram, and there's no kind of extra information hidden in here in which is not visibly present in the diagram. There isn't though, so basically we don't even really need to pay attention to this section here. We can only look at the diagram. So we need to find the area of the sector ZYW for part A. So this is the sector ZYW here, and this is a pretty easy question because this is just a sector that we just need to find the area of. Remember that it's not given to you in the formula booklet. The area of a sector is half r squared theta if theta is in radians, which it is here. R is equal to 5 and theta is equal to, in radians, 0.7. So we just need to sub these values in. So A is equal to half times r squared, which is 5 squared, times theta, which is 0.7, which if you put it into a calculator, the area of the sector is equal to 8.75. Now it is technically in centimeters, so I guess you can technically write it in centimeters cubed, but it doesn't really matter that much. You're not going to lose marks if you don't put that. So for part B, we need to find the area of the flag. So aka it says that the flag is the whole shape. So we basically need to find the area of this whole shape. We've already found the area of the sector here, so we just need to find the area of this triangle here. Now, ideally, we would probably like to use A is equal to half AB sin C, because this is the easiest way to do it. Now, there's a couple of things that we could do here. Firstly, we know what the length of this side is here, because we know that the radius of the sector is 5, so therefore this side is going to be 5 as well. So therefore the length of this side is also going to be 5, which is in the triangle. And we can also figure out this angle here, because this is a straight line. You can both see it, and it also says that X, Y, and W lie on a straight line. So as this is a straight line, these angles here should add up to 180 degrees, or in radians, pi radians, okay? And we know that there's made up of two angles, this angle and this angle, and we know this angle here. So this angle is going to be pi, or 180 degrees if you want to think about it like that, pi minus 0.7, which is equal to, if you put it into a calculator, 2.442. The kind of decimal places, it says to give the answer in two decimal places. In your working out, the decimal places that you use don't really matter too much, as long as it's more than 2. So there's not going to be like, if you use one decimal place, you might get some error in your answer. So just as long as you do more than 2 decimal places in your working out, it's fine. So this angle here is 2.442, and that means we can now use this formula here, because we have this side, and the angle in between. So A is equal to 7, B is equal to 5, or vice versa, and C is equal to 2.442 radians. So the area is equal to half times 7 times 5 times sin of 2.442. Again, you can use radians in this sin here, as long as your calculator is in the radians mode. So your calculator knows that you're putting this in as radians and not degrees. And if you put this into your calculator in the radian mode, you get out an answer of 11.27 to 2 decimal places. So that is the area of the triangle. But the actual question wants us to find the area of the flags. The whole thing, so all we do is do 11.27 plus the area of the sector, which we figured out in part A. So 11.27 plus 8.75, which if you put into a calculator is equal to 20.02 to 2 decimal places, and you can also do centimeters squared if you want to. And that's the final answer. So for part C, we need to find the length of the perimeter of the flag. So aka this is all of these sides around the shape, like this. We don't need to figure out this side here because it's not part of the perimeter. It's the length of the perimeter of the flag, so around the shape like this. So okay, we need to figure out 4 sides. This one, this one, this one, and this one. Well, we already know 2 of them. We already know this one is 7, and we already know this one is 5. This here is an arc of this sector here that we've talked about before, and we know from this video the arc length is equal to r theta, where r is equal to the radius, which is 5, and theta is equal to the angle in between the radii, which is in radians, which is 0.7. So therefore L is equal to the radius, which is 5, times 0.7, which if you put into a calculator is equal to 3.5. So this side here is 3.5. And we need to figure out this side here. And we can do this because we know this side, we talked about before that this side is 5, and we figured out this angle before as 2.442. And if we have 2 angles and an angle in between, we talked about how we can find out the area. The other thing that we can do is you can use the cosine rule in order to find the side opposite to the angle. So the cosine rule, remember, is a squared is equal to b squared plus c squared minus 2bc cos of a. This isn't given to you in the formula booklet, so you have to remember it, where b and c is just one of these can be interchangeable, and the a here is going to be this angle here, 2.442. So therefore a squared, which is going to be this, is equal to b squared, which let's just call this side b. So it's going to be 7 squared plus, and then 5 squared, minus 275 cos of a, which we figured out before that this angle here is 2.442 in radians. So again, make sure we calculate in radians mode. And if you put this into a calculator, therefore a squared is equal to 127.557, but this is squared, so we need to square root it. So therefore a is equal to the square root of this, which is equal to 11.29. So this side here is 11.29, and therefore we can figure that perimeter by adding all of these together. So it's going to be 7 plus 5 plus the arc, which is 3.5, plus the other side of the triangle, which is 11.29. And if you put this all into a calculator, you get the answer of, to two decimal places, 26.79 centimeters. And that's the final answer. So here's another example question where we're given this shape here, ABC, which is a sector. You can see it's a sector. If you just want to cast it out like this, we've got these two sides here, and then we've kind of got the curve here, the arc like this, with radius of 7 and this angle here of 0.8 radians. And we need to firstly find the length of the arc BC, so the length of this arc here, which is very easy. Remember that the length of an arc L is given by r times theta, if theta is in radians. R is equal to, it tells us the radius is 7 and theta is 0.8 radians, like this. So therefore L is going to be equal to 7 times 0.8, which if you put into a calculator is equal to 5.6. And if you want to, it's in centimeters, but it's not really too important, the centimeters part. And then for part B, we need to find the area of the sector ABC, which is very easy. The area is equal to half r squared theta, and we've already talked about what r and theta are. So therefore the area is equal to half times r squared, which is going to be 7 squared, times theta in radians, which is 0.8. So therefore the area, if you put it into a calculator, is equal to 19.6 centimeters squared. So for part C, we need to find the perimeter of R. So R is this shaded region here. So we need to find the perimeter. So we need to know this side, we need to know this side, and we need to know this curved side here. Okay, we already know this curved side because we figured it out in part A. It's 5.6. Now we're told in this section here that point D is the midpoint of AC. So point D is the midpoint of AC. And as we know that this whole thing is a sector, aka it's kind of like part of a circle, and we are told that this has a radius of 7, therefore AC, the whole thing, is also going to have a length of 7. AC is going to be equal to 7 because it is also a radius of the sector, and as D is the midpoint, therefore this is going to be split up into two equal parts of 3.5 here and 3.5 here. So we know that this side here is 3.5. So now we just need to find this side here, and we can do this because we have two sides of this triangle here. We have two sides and the angle in between. So we can use the cosine rule. So the cosine rule is a squared is equal to b squared plus c squared minus 2bc cos of a. So a squared is going to be equal to, so we can use b and c interchangeably, so I'll just call this b. So it's going to be 7 squared plus 3.5 squared minus 2, 7, 3.5, and then cos of 0.8. Remember to put your calculator into radian mode if you want to keep this as radians. So therefore a squared, if you put this into your calculator, is equal to 27.11, but this is a squared, so therefore a, which is going to be this side here, is equal to this square rooted, which is equal to 5.21, like this. So this side is 5.21, so therefore we have all the sides. So the perimeter is going to be 5.6 plus 3.5 plus 5.21, which if you put this into a calculator, it's equal to 14.31, but it says it wants it to three significant figures, so it's going to be 14.3 centimeters. So for part D, we need to find the area of R, and R is a segment. Now remember, we talked about before how to find the area of a segment. We need to find the sector, and we need to find some sort of simple shape and then minus the areas from each other in some way, so we're just left with the area of the segment. So first of all, we need a sector, and we've already talked about what the sector is. The sector is the entire thing here with this curve here and these two radii, and we also need to find some sort of simple shape, and we've already discussed about this triangle here like this, and hopefully you can see that the whole thing is the sector. So if we do the area of the sector and we minus the area of this triangle, that means that we will just be left with R. So this is what we're going to do. So the area of the sector minus the area of the triangle, and we'll just be left with R. The area of the sector we figured out before, and the area of the triangle we can do because we have two sides and the angle in between them. So we can use the area of a triangle, which is equal to half A, B, sin C, like this, where A is equal to 3.5, or it could be the 7 as well, the B is equal to 7, and the C is equal to the 0.8 radians. So therefore the area of the triangle is equal to half times 3.5 times 7 times sin of 0.8 radians. Again, make sure your calculator is in radians, and therefore the area of the triangle, if you put it into a calculator, is equal to 8.788, and we can therefore figure out the area of R by doing the area of the sector, which is 19.6 up here, minus the area of the triangle, which is the 8.788. Again, the significant figures of how we figure out the triangle doesn't matter too much as long as it's more than what the question is asking, so we don't make any kind of like errors in terms of what we're rounding. And if you put this into a calculator, this is equal to 10.812. It wants it to three significant figures, so therefore it's 10.8 centimeters squared, and that's the final answer. So here's a couple more questions on arc length and sector area that you can have a go at if you want to. So pause the video, have a go, and I'll go through the answers in about 5 seconds. Okay, so for question 1, we're given the shape ABC, which is a sector. So this whole thing here is a sector like this, and we need to find the length of the arc BC for part A. So this is this arc here, so this is just the arc of the sector. So remember that the length of an arc is given by the equation r theta, where r is the radius of the sector, which is told is 6, and theta is the angle here, which is 0.95, and it's told that it's in radians. So therefore the length of the arc is equal to 6 times 0.95, which is equal to 5.7 centimeters. So for part B, we need to find the area of this entire sector again. So again, this is quite easy. We just need to sub the values into the formula. The area is equal to half r squared theta, like this, where r is equal to 6 and theta is equal to 0.95. So for the area is equal to half times r squared, which is 6 squared, times 0.95. And if you put this into a calculator, the area is equal to 17.1 centimeters squared. So for part C, we're introduced to this point here, which is D. And the important thing about this point is it makes this side and this side the same length, and this, therefore, this triangle now becomes an isosceles triangle, because remember, one of the features of an isosceles triangle is that two of the sides are the same length. So this triangle is an isosceles triangle, and one of the other features of an isosceles triangle is that this angle and this angle are going to be the same angle, because that's just one of the features of an isosceles triangle. When it is the angle here and here, these are going to be the same, so therefore this angle here is going to be 0.95 0.95. And now we can figure out this angle, because remember the angles in a triangle add up to 180 degrees. Now because we're working in radians, we're instead going to say that angles in a triangle add up to pi radians, because remember 180 degrees is equal to pi. So therefore we can figure out this angle here by it being pi minus the other two angles, 0.95 and another minus 0.95. And if you put this into a calculator, this is equal to 1.242. So this angle here is equal to 1.242. And now we can use the sine rule, because remember the important thing with the sine rule, go back to the video if you need reminding, the important thing that we need in order to use the sine rule is we need this opposite side and angle here, which we have. We know that this side is 6 and we know that this angle is 1.242 radians, and we can also figure out the length of this side, which is the side that we want AD, because we know its opposite angle here, 0.95. Now a reminder with the sine rule, the best tip is if you're trying to find the length of a side, then use the version with the length on top of the fraction. If you're trying to find an angle, we're not trying to find an angle here, but if we're trying to find this angle, for example, use the version of the sine rule with the angle on top of the fraction. Because we're trying to find a side, we're going to use the version of A over sin A is equal to B over sin B, which is equal to C over sin C, like this. So we have this opposite angle and side here, so therefore this is going to be, so the side is going to be on top, so it's going to be 6 over sin of 1.242 radians, like this, and this is going to be equal to, so we need to find this side here, so let's just call this AD, over sin of the opposite angle, which is this angle here, 0.95, times both sides by sine of 0.95 to get rid of this denominator here, so it becomes 6 of sin of 0.95 over the sin of 1.242, and this is equal to AD, this side here. And if you put this into a calculator, make sure your calculator is in radians, because we're working in radians here, not degrees. If you put this into a calculator to 3 significant figures, this is equal to 5.16 centimeters, which is what's required in the question. Now really quick, another method that I saw in the answer book, I didn't actually think of doing it this way, I did it the way I just shown, is you could draw a right angle triangle here like this, and say that this side here, because this is 6, this is therefore going to become 3, and this is going to become 3 as well, and therefore you have an angle and a side and a right angle triangle, and therefore you can easily just find the length of this side. I didn't think of that way, but it's a quick way if you wanted to do it like that as well. So for part D, we need to find the perimeter of R, and R is this shaded region here, so we need to find the length of this side, and this side here. Okay, well we know the length of this arc because we figured it out in part A. The length of it is 5.7, and we know the length of this side here as well because it is the same length as this side, AD, and we figured out in part C that the length of AD is 5.16, so this is 5.16, like this. So now we just need to figure out the length of this side here. Now we know that AC, the entirety of AC, so this whole thing here, is the radius of the sector, and we know that the radius is 6, so we know that AC is equal to 6, and we also know that AD is 5.16, so AD is equal to 5.16. So this whole thing is 6, and then this little section here is 5.16, so therefore the length of DC is just going to be the length of the whole thing, 6, minus the length of AD here, which is 5.16. And if you put this into a calculator, this is equal to 0.84. So the length of this side is 0.84. So to get the perimeter, we just need to add all of these together. So it's 5.16 plus 5.7 plus 0.84, which if you put into a calculator is equal to 11.7 centimeters. And then for part E, we need to find the area of R. So we need to find the area of this segment here. Now remember how you figure out the area of the segment. Firstly, you need to find a sector, and we've talked about already that this whole thing is a sector here. So we found the sector, and then we need to find some sort of simple shape, and we talked about already that there is a triangle here, an isosceles triangle here. So we have a triangle, and hopefully you can see that the whole thing is the sector. So we're going to do the area of the sector minus the area of this triangle here. So the area of the entire sector minus the area of this triangle here will just leave R remaining. So the area of the triangle. So we already know the area of the sector. We figured it out in part B. It's 17.1. And the area of the triangle, we know that AD is 5.16. And that means we have two sides and the angle in between, which means we can use the area for a triangle. Area is equal to half A, B, sin C, like this. Remember, this isn't given to you in the formula booklet, where A is equal to 6, B is equal to 5.16, and C is equal to 0.95 radians. So the area is equal to a half times 6 times 5.16, the two sides, and then the angle in between, sin of 0.95. Whenever you get two sides and the angle in between, you should be thinking about, you can figure out the area of the triangle, or you can use the cosine rule. So in this instance, we need the area of the triangle, and if you put this into your calculator, you get a value of 12.59. So that's the area of the triangle. So therefore, in order to get the area of the segment, we need to do the area of the sector, 17.1, minus the area of the triangle, 12.59, which if you put into a calculator is equal to 4.51. Once it's to two significant figures, so it's going to be 4.5 centimeters squared. So for question 2, we're given this quite complicated looking shape here, and we're given this info here, and all the info here is in the diagram here. And for part A, we just need to find the area of the sector BAC. So the area of the sector BAC, so it's BAC, and then it has this arc here. So we need to find the area of this sector, which is really simple because we can see that the radius is equal to 6 and we have this angle here. So we use the formula for the area of a sector. Area is equal to half r squared theta, with r equal to 6 and theta equal to this angle here between the two radii, which is 2.2 radians. And theta is in radians, therefore you can use this formula. So therefore the area is equal to half times 6 squared times 2.2, which if you put into a calculator is equal to 39.6 centimeters squared. So for part B, we need to find the size of the angle DAC. So the angle DAC is DAC like this, so it's going to be this angle here. And the important thing with this question is realizing that because the length of this side of the triangle is 6, and it's the same here, because they both have a side that's 4 centimeters, and it tells us that the lines DB and DC are equal in length, so DB and DC are equal in length. Therefore, these two triangles are going to be the exact same, and therefore, because these triangles are the exact same, this angle here DAC and this angle here DAB are going to be the same angle. They're going to be the same angle in radians or degrees. And this is really helpful for us figuring out the question, because we have 3 angles here, and we know that angles around a point add up to 360 degrees. So therefore, this angle, this angle, and this angle are going to add up to 360 degrees. As we're working in radians, remember, 360 degrees is equal to 2 pi radians. So aka angles around a point add up to 2 pi radians. So what we can do to get the length of these two angles here, we're going to do 2 pi minus 2.2, and if you put this into a calculator, this is equal to 4.083. So therefore this angle and this angle added together is going to be the remaining 4.083, and as we know that these two angles are the same, therefore we're just going to divide this by 2. So 4.083 divided by 2 is equal to 2.042. So therefore this angle and this angle are going to be 2.042. Once it's a three significant figure, so it's going to be 2.04, and then you can put radians at the end if you want to, but it's not really that important. So the size of this angle DAC is equal to 2.04 radians. So for part C, we need to find the complete area of the logo design, aka the area of this entire shape here. Well, we already know the area of this sector here, we figured it out in part A, so we just need to figure out the area of the two triangles. And as I said before, we figured out these two triangles are the same, so we only need to figure out the area of one triangle and then just times it by 2. So let's focus on this triangle, and we figured out before that this angle here is equal to 2.04 radians, and therefore we have two sides and the angle in between. And remember, whenever we see this relationship here, we can always use the formula for the area of the triangle. Area is equal to half AB sin C, like this, where A and B are the two sides of the triangle and the angle in between is C. So whenever you see the two sides and the angle in between, you know you can use this formula here. So the area is equal to half times A, which is 6, times 4 times sin of 2.04. Remember, you just put your calculator into radians mode if you're going to be working in radians, and if you put this into your calculator, you get a value of 10.7. So that's the area of this triangle. So the area of the entire shape is going to be the area of the sector, which we figured out before. That's 39.6 plus the area of this triangle, which is 10.7, plus the area of this triangle, which is the same area as this triangle, so they're the same triangle, so another 10.7. And if you put this into a calculator, you get out a value of 61. So it's 61 centimeters squared.